So let's talk about the packet here. Let me first start off by going to the very back. I want to highlight the rules because these are all the rules, but I want to just highlight the ones that I want to focus on. So, and these are also the most important ones. Uh, we understand also that if we want to go through use substitution, we have to be able to recall all of our derivative rules as well. So, this is on the very back page. I'm going to highlight the ones that I want you guys to make sure you know. Obviously, derivative for power rule, you're going to have to know that. Your trig derivatives, okay? We learned that from first semester. So, and also I think it's really important that we memorize these rules because if we know these 6 rules, we also know our 6 trig integral rules, right? Don't have to worry about um, memorizing 12 rules if we can just have 6 and know how to get to the other 6. Derivative for e to the u, derivative for natural log of u, and then don't have to worry about these. Okay. So that's on the derivative side. Everybody good? Now on the integral side, obviously power rule, trig integrals, but again, we don't memorize these, right? We just build them off of our trig derivatives. You have these 6 memorized, the integral rules, you're just going backwards, right? Antiderivative cosine is sine, antiderivative secant squared is tangent u. So there's no need to memorize these. Are we good with that? Okay, 1 over u du, we just learned this. This is involving natural log. E to the u, we briefly talked about this, but well, the nice thing is that if the derivative of e to the u is e to the u prime, or e to the u times u prime, then the antiderivative of e to the u is e to the u plus c. So this, we can, technically this is what people say the easiest rules are because there's no change, right? The integral of e to the u is just e to the u. But if this u substitution, we do have to make sure that our x's cancel out, we keep track of our coefficients, but ultimately the rule is not changing. I'm not going to have us worry about the a to the u rule. We can take that out. There are trig integral rules involving natural log. I'm not going to focus on that on the test, so take those out. Arc trig is intimidating, but I'm just going to have us focus on this, okay? Just arctangent, okay? The amount of material that we're going to cover here, I just want to focus on the ones that have the highest chance of making it on the AP exam, okay? And I'll just focus on that. Okay. If you go to page, oh wait, did I provide that? No, I'm sorry. I don't think I did. Yes, yeah. So in your packet on page 59, these have all the rules that you can use as a blank practice sheet to kind of help see if you remember your rules, right? So that's just there if you want to use it. But everybody good with the ones that I want you guys to focus on? Okay, derivative and integral rules. Okay. I'm just focusing on the ones that that are definitely going to show up on the AP exam. Okay, the ones that are not so obvious, maybe we can revisit them down the road. But just going to have you guys focus on for derivative, just the big 3: power rule, e to the u, natural log, and then also trig derivatives. The more obscure rules, I'm going to leave those out. Okay, let's go to the front here. I have on the board the types of problems that I want us to be able to do. So the first 2 pages have all the rules or have all the types of problems, but it doesn't include the natural log e to the u. So I have that later. But Let me highlight a couple of problems that we're going to do. This one, how about this? For each problem, can we identify the first steps? Okay, what type of problem it is, and then we can always go back and do it. I think that's the hardest part, is looking at the problem and recognizing, wait, what do I do first? If you can figure out the first step, then I feel like everything falls in line a lot easier. Okay, so can you tell what type of problem this is? Right, so there's only one term in the denominator, that's the giveaway, right? So this one we can expand and just rely on power rule. Okay, number two, because expansion doesn't work, right? We always consider expansion first. Okay, doesn't work. We know it's u sub. Okay, what's our u value? Yeah, so that and will this come out cleanly for us? Yeah, that degree is favorable, right? X squared, the derivative is 2x. Okay, so once we go through substitution, make sure x's cancel out. Okay, all right, good. We'll definitely redo all these, all right? I just want to make sure, okay, can we identify the first step? And I think that's the hardest challenge. Number 3 here. It looks like u sub, but we should always check for what? When we expand this through, yes, there's nothing preventing us, right? The square root is with the x, it's not with the whole expression. This is fine, right? I can distribute my way through and just rely on power rule. So it looks, I know we have to kind of remind ourselves that not every parentheses is u substitution. A lot of them are, but we never want to forget the first thing is expand, right? If I cannot get that first condition to pass, then your second option is u substitution. Yeah, question?
Oh, we like accidentally do substitution there.
Yeah, it's not going to work. Most of the time, it's just you're gonna figure out, you're gonna be like, wait, something is not clicking here. I'm not able to get everything to go away. And that's because it's meant to be a expansion problem, right? We don't do u substitution unless it's complicated enough where we need it, right? And it's not going to work for easier problems, right?
How do you know like what you can?
We have to look at the problem, right? First, is it possible to expand? Right, this one is possible, right? I can distribute this through. It's not like this problem where I cannot expand. So think about PEMDAS, think about your expansion, think about what is algebraically possible. The other thing is, if the parentheses has an exponent that is more than 2, that's also a giveaway that you gotta go to u substitution. So hopefully you can tell 1 and 3, these are expandable, right? These are not anything that is too hard for us to algebraically clean up, rely on power rule. Okay, how about number 4? Substitution, right? There is no expansion with secant squared. And also, we do have a rule for secant squared, but this is a little too complicated. Yeah, this is u sub. What's our u value? 5. U sub. Because expansion doesn't work. What's our u value? 7. Is this going to work out initially, though? Are things going to clean up nicely? No. This is too high, so we got to do a little bit of what we call change of variable. We got to rearrange this equation, right? All that process. So we'll go through that. Okay, how about number 6? U sub, that exponent is too high, right? I mean, we could expand, but we said that if it's anything higher than 2, we want to explore a different option. Okay, so this is u sub. But we got to eventually do what? Right. But do the 1 and 2 get involved at the beginning?
No.
Right. Right. So you go through u substitution, you find the answer, you pretend like the bounds are not even there. You get to the answer, and then right when you're about to put that plus c, drop the plus c, you do the half bracket, and then you plug in the upper and lower bound. Okay, so this comes at the very, very end with definite intervals. Okay, good. Next page. Find the derivative for this messy expression. This is, yeah, remember second theorem? We can cancel out and go through all that process. So I'll do SFTC. This is the second fundamental theorem of calculus. This goes for both 7 and 8. Okay, number 9 and 10, we haven't gone through these yet. These are absolute value functions. We're going to go through this from a geometric shape perspective. So hopefully you'll find this easy. We'll go through that in a second. This one is particle motion, but really you're just taking the second derivative to the first derivative. A plus c shows up, you solve for c, you plug in. So we'll go through this together. And this one is average value. So this is average value theorem. We'll go through this as well. So I'm going to focus on the problems that I haven't really gone through in detail, but I would like for you guys to do the first page for homework. Okay, I feel like those are manageable. The keys are attached. So okay, we'll do 9 through 11, 9 through 12 in a second. But I want to flip over to the natural log exponential type problems. So this is I didn't put page numbers here, but it says worksheet 2. These are u substitution problems involving 1 over u and e to the u. So remember, 1 over u, power rule is just not going to work, right? If you bring that u up to the top, it's going to end up with u to the 0 over 0. We know that doesn't work. So okay, number 2 here, expansion doesn't work. What could be our u value then? Yeah. And then this will turn into a 1 over u problem, and then we do natural log. Okay. Okay, let's go to the back here. 7 and 8. We can't rely on power rule because why? Cannot expand, right? So now we know that this is not good for power rule. Is this good for u substitution? Degree is not going to match up nicely. The degree is 1 higher than the denominator. This is a linear term. What do we do here? This is specific. This is synthetic division. Yeah, we do synthetic division, and then we split it up, go through power rule, and then there's that one last term which requires natural log. So
Like, how would it, like, what would make it a U-sub problem, like, denominator?
yeah, usually what happens is if the denominator has a higher degree than the numerator, that's a good fit for u sub. Yeah. Okay. Number 11. Know what this one is. U sub. Now, this is what we're trying to target here. We're trying to make it look like e to the u. Because if e to the u is e to the u plus c, then that's a perfect match, right? Is that exponent going to produce a derivative that will match this x?
Yeah.
Yes. Coefficient aside, we can pull that coefficient aside and do that. So I want to get to one of that with you. So 11 and 12, these are good problems for us to practice. And again, the bounds are not a factor until the end, right? We don't do anything with the bounds. We pretend the bounds are not there. We take the indefinite integral before we do the bounds, okay? All right, so we'll come back to that. The keys are attached, so those are problems I want you to focus on. Worksheet 3, same idea. Worksheet 4, I highlighted the problems that I want us to be able to do. So number 7, this one here. This is all the way back, worksheet 4. This is the type of problem that I want us to be able to do here. Now, can we expand this one? Not favorable, right? Can I go to u substitution? Not a good match either. Now, look at the degree here. Degree of the denominator is what? numerator is degree what?
0.
There's a what? There's a gap, right? If there's a gap, the denominator is higher, what are we looking to match itself with? This is our trig, yep. But it's an arc trig with a denominator not in the binomial factored form, so we also got to complete the square here.
So like, the degree in the denominator is higher than so like,
Right, sorry. If the denominator degree, if the denominator's degree is higher than the numerator by one, that's a good fit for the numerator because you know the derivative is going to produce, if it's x squared, it'll become 3x in the numerator is good. But if there's a gap, x squared versus 0 or x to the fourth versus x squared, we know that gap won't be fulfilled with u substitution. All right, so on the board here, okay, I think I highlighted all the problems in the packet here. So power law, u substitution, natural loss instead of division, exponential equal u, arc trig complete the square, bracket intervals, partial motion, average value theorem, trig intervals with u sub, absolute value depth intervals. We'll go through that. Haven't gone through that yet. Second theorem of calculus, change of variables, and stuff. So those are the topics we're going to focus on in preparation for the test. Okay. Okay. One last thing here. I do feel like we're a little rushed. I will we'll spend tomorrow finishing up review, maybe do a little bit of review Wednesday. I'll push it to Thursday. Okay, so Thursday test. But I do need to start the calculator portion review on Wednesday, but it kind of buys you an extra day on your own to review. Okay. I don't know the calculator portion yet. It'll be sometime next week, but I only want to spend 2 days in class going over calculator portion. It's very straightforward. I'll tell you exactly the 3 types of problems that you're going to study. I'll give you a packet for it as well. It'll be sometime next week. Okay, sometime next week. But if we need more time, then we'll start the next unit, buy you some time. But I'll push this out to a time a day next week that where you're comfortable. Okay, but I'm only going to spend 2 days in class going over the calculator portion. All right, so let's go over the parts that I want to go over with you. So let's go to page 2. Number 9. Now, absolute value feels intimidating. We could go through this using power rule, but I have a much more efficient way of getting through this where much more visual. So let's focus on this graph first. What do you know about an absolute value graph? What does it look like? Looks like a V, right? Looks like a V. You know where that vertex is based off of this equation? Good. Negative, well, not 0, 2, negative 2, 0, right? That's the vertex. So whatever is inside, you're going to take the opposite sign. It's going to shift the graph to the left 2 units, and it's going to be on the x-axis. So if I can draw the graph, that doesn't have to be accurate, except to just draw the graph where at least you see it in front of you. Now, you see the bounds involved, right? So the bounds tell us that we're essentially finding the area between the graph and the x-axis. So again, there's no need to be super accurate here. You just have to be able to, this is negative 2 here, negative 3, negative 4, negative 5. So, and then from negative 2, I'm going to go all the way over to 6. 1, 2, 3, 4, 5, 6.
The absolute value function always going to be linear.
That's right. It's always going to be nice and linear. I mean, there are absolute value with squares inside, but I'm not going to give you those.
Okay.
Yeah, it will feel like, yeah, it's basically linear. Now, what shapes do you see in front of you here? That's it. We just add the areas of those 2 triangles, and that is your answer. Okay. Now, what's the area of a triangle formula? 1/2 base times height. Now, how can I find the height at these ends of the triangles? Good. Plug in the x value directly into the function, and you know absolute value will just turn it positive. So if I insert -5 in for x, what do I get? Absolute value of -3 is 3. So I know this order pair is at -5, 3, and that 3 represents the height of that first triangle. How can I find the height of the second triangle? Plug it in, and I get what?
8.
My order pair is 6, 8. 8 is the height of the triangle. So 1/2 base times height, we do that twice. What's the base and height, or width and height of my first triangle? 3 and 3. 8 by 8, right? Add that up. Hopefully we consider this easy, right? So yeah, it's whenever I see a test with this left blank, it kind of, yeah, I'm just like, wow, this should be an easy problem, right? If we understand the process, you're not to go through a whole calculus. If you just visualize it, draw the triangle, find the height, you should be able to get to the answer, right? Okay, so let's do one on our own so that we feel really confident. So, you're not, so this, this will feel like, hopefully this feels like an easy, gimme, problem on the test. So let's make sure that we are comfortable. So figure out what the graph looks like, figure out where the vertex is, draw your graph, extend your graph to the ends, and then you can plug the ends into the function, get the y values. The y value will be your height, and find the base and the height of each of the triangles and add up your triangles. Check your answer on the next page as well. Okay, check the board, or check with the key on the next page. Are we good with 10? Make sure that you know how the graph is looking. Your graph is going to shift in the opposite direction of the sign that you see. It'll shift to the right 4 units, so you know your vertex is at 4, 0. Extend the graph in the V shape in both directions until you hit the x value bounds of -2 and 7. And then you can plug -2 and 7 back into your original absolute value function. Get the heights. Once you get the heights, then do 1/2 base times height for each triangle and add up your 2 areas. Okay. Are we good here? All right, so let's look at number 11. Now let's go back. Let's review from first semester here. let's say I had a position function as x of t. What's the derivative of, position? Velocity, right? X prime, which is velocity. And then what's the derivative of velocity? Acceleration. So it's b prime of t or a of t. So if we understand the derivative process, we should be able to make our way up the chain. So if I know the derivative of position is velocity and the velocity is acceleration, what's the antiderivative of acceleration? Velocity, right? So I can say the antiderivative of acceleration is simply v of t plus what? C, yeah. So we're going to use this to help us create a general equation. We can plug in the order pair to solve for c. We can get that updated, and then we can go through that process again. The antiderivative of velocity will bring me up to what? Velocity, yeah. What's velocity's antiderivative? Position, right? So x of t plus c. Right. So we're just going through. We're just undoing our derivative process. So let's see if we can go try number 11. 11 is if acceleration is given, and you have two order pairs that will help you solve for c, find it below. So let's find v of t. So we know v of t is just the antiderivative of acceleration. Okay, so we go through power rule. What does 4 become? Plus c. Okay, so we're going to pause for a moment. We're going to clean this up. Is there something available for me that can help me solve for c?
Yeah.
Which order pair? Yeah. I have the order pair at the velocity level, so plug -1 in for t, plug 9 in for the velocity variable, and then solve for t. Sorry, solve for c. Once you solve for c, we can update the equation, and then we can repeat the process to get from velocity up to position. So when I made the substitution, replace v of t with 9, and replace -1 in for t, I solved for c, and I got c equals 0. So plus 0, I can just let it drop out. So my velocity feels like as if it doesn't have a constant because that constant is plus 0.
Be any like total distance question or like
Not until the calculator portion.
okay.
I'm not gonna put it on the calculator. All right, so we're halfway there. What can we do next to get the position?
Same.
Take the power rule, take the integral of velocity, and then I'll produce x of t. Make sure the plus c shows up. Once that plus c shows up, use the order pair to solve for that plus c. And then you have your, so we call the plus c, if the equation has plus c in it, we call this the general solution. And if that plus c is resolved with a specific number, then we call that a specific solution. Okay, let's try that, see if we can finish off that piece. And then we'll look at them both. I use plus K, because, but you can use plus C again, it doesn't matter, that's no big deal. I just didn't want that plus C to be, yeah, two plus C's, because those constants are at different levels, but usually what happens is, K is another, if we go into the end of it twice, plus C can be used for the first, or it can be plus C for two. But this is basically my constant, for my position function. But then, order pair can be inserted in. We can solve for our constant. My C of two, or my K is one, and then I can update my equation level. Okay, let's look at number 12. At this point, you guys also have the key that you guys can look back on. Okay, so let's look at number 12 here. If you guys want to kind of highlight my graph's a little bit faint here, but we see that these are all nice geometric shapes here. Remember, okay, we're dealing with area. It says the graph below consists of semicircle, triangles, and squares. Find the average value of f. So average value is average value theorem. So it's just basically area divided by width, but it takes on this form. So what's our A and B value? 19 and 5, so we just put all that in. We're basically just finding the area between the graph and the x-axis. That's important. There are more shapes that may be throwing you off, but remember, you're only shading what's between the graph and the x-axis. If you are shading other shapes, they're not part of your diagram. So that's something that I see some students just mess up on. They shade in the wrong portion, and then they end up finding the area that is not involved, and then that throws their answer off. Remember, you're only looking at what's between the graph and the x-axis. There may be other shapes that you see, but they're not what we're working with. Anything above the x-axis, we want to maintain, keep that at what? Whatever below is negative. So we just add up the positive and negatives. That represents our definite integral, and then we divide that by whatever, or multiply by the fractional b minus 1 over b minus a. Okay, so triangle is 1/2 base times height. Square is width times height. Semicircle is 1/2 pi r squared. And then you got a triangle, 1/2 base times height, and a square. So there's no need for calculus steps here because these are all nice geometric shapes. So once we find the area, we can replace that number here and then multiply or divide by 7.
Not nice geometric shapes, you'll give up.
Right. If it's not a nice geometric shape, I'll give you the function, but it'll be that. Any questions? So, tomorrow, I'm not gonna, be here. Well, I'll be here in the building, but I'm gonna be spending tomorrow's, as a day for me to do some catch-up work. So, I'm gonna have Mr. Bola come, and he's gonna sub in for the class tomorrow, and I'm gonna have him go over problems with you, from worksheets 2 and 3. So I'll have him go over synthetic division, I'll have him go over, use substitution involving exponential and, natural log, as well as, problems involving arc trig and completing the square. Okay, so some of the newer topics I'll have him go over. But for homework, I'd like for you guys to finish worksheets, pages 1 and 2. We did most of 2. It's just the top portion with second theorem. I'll send out a reminder this afternoon, but I highlighted the first step for you, so I want you guys to practice, work through that, and then tomorrow, I'll have them go over, those specific kinds of problems, and then I'll also make it available where you can, have them go over any problems on the first page if you have any questions. But tomorrow, give you guys a chance to practice some of the newer concepts. And then Wednesday, we will do some final review, but I do need to start the calculator portion. But I'll give you another review to kind of give you some more practice problems to do, but hopefully it really take these 2 days to prepare for your test so that you feel ready by Thursday. Okay, all right, come get your phone. So tonight, your homework is pages 1 and 2. Use that with part of the because if we look ahead, find that my U value is something where the derivative is going to be much. It's going to be like change.
So what if we just take it next week? Oh, you want to use
Can test if I will propose. Right. Like, U value is this. There's another secant that's going to come from the derivative. Yeah, so this is right. It's a little bit of like, oh, wait, all this is probably going to fit. And the weight, it's not always a guarantee, but I like to see where the business is going. Yes, and look to see what available interval rules you have. Because even if everything goes away, if I don't have an interval rule for that specific setup, then I don't have a rule. But I do have a rule for secant square, right? I do have this.
I was gonna say, trash, but I think. But you feel like trash, I bought it. Also for one of the gas stations, that you are let's say, and you want more ice, more much. But you need to.
I'll see you guys on Wednesday.
What you got?
I am thrilled.
Yeah. Like wavelengths. I don't